Picture this. It's 1969, and you're at a drag strip outside Mexico City. A beat-up Volkswagen Beetle pulls up to the starting line next to a Plymouth Roadrunner with a 446-pack. The American muscle car owner is laughing. His buddies are taking bets on how badly he'll destroy this little German economy car. The tree lights up green. The Beetle launches hard, chirping its tires through first and second gear. By the time they cross the quarter-mile mark, the VW is a full car length ahead, running a 12.8-second pass. The Roadrunner driver demands to see what's under the hood, convinced there's a Porsche engine swap or hidden nitrous system. What he finds instead is an air-cooled flat four that looks almost stock. Almost on its downer, this is the story of Carlos Gonzalez, a Volkswagen dealer mechanic who achieved what engineers in Wolfsburg, Germany, said was physically impossible, extracting over 200 horsepower from a naturally aspirated Beetle engine without forced induction or chemical assistance. At a time when the factory claimed these engines couldn't safely exceed 100 horsepower, Gonzalez was building street-legal Beetles that embarrassed big block V8s at the drag strip. But here's where it gets interesting. Gonzalez didn't just build fast engines. He systematically re-engineered every weakness in the VW flat four design, creating solutions that would influence automotive engineering for the next 5 decades. His innovations didn't just transform Volkswagen performance, they changed aircraft engines, influenced Formula V racing worldwide, and spawned a multi-billion-dollar aftermarket industry that exists to this day. To understand why Gonzalez's achievement was considered impossible, we need to examine what Volkswagen was building in 1969. The Type 1 Beetle came with a 1500cc flat four, producing 53 horsepower. That's not a typo. 53 horsepower from an engine designed in the 1930s, essentially unchanged since Hitler approved the original blueprints. The compression ratio was a conservative 7.51. The single-port cylinder heads flowed about as well as breathing through a coffee stirrer. Maximum safe RPM, according to VW, 4,500. Push it harder, and you'd scatter connecting rods across the highway. And the engine used a single carburetor the size of a shot glass. The cooling system consisted of a fan belt that loved to break and cooling fins that clogged with oil residue. The crankshaft was pressed together from multiple pieces, literally held together by friction. The case halves were magnesium, soft enough to carve with a pocket knife. Every Volkswagen engineer would tell you the same thing. This engine was designed for economy and reliability, not power. Try to double the horsepower, and you'll be walking home. Meanwhile, in his small shop behind a VW dealership in Mexico City, Carlos Gonzalez was studying these engines with the intensity of a surgeon examining X-rays. He'd been working on Beetles since 1958, and by the mid-1960s, he noticed something interesting. Mexican customers were different from Germans. They didn't just want reliability, they wanted to keep up with traffic on mountain roads, fully loaded with family and cargo. They needed power at altitude, where Mexico City's 7,300-foot elevation strangled engines designed for sea level. And Gonzalez started conservatively. He'd port the cylinder heads slightly, increasing airflow by maybe 15%. He'd advance the timing a few degrees, bump the compression half a point. These minor modifications might add 10 horsepower, enough to satisfy most customers. But then came the watershed moment. A wealthy customer walked in with a special request. He wanted his Beetle to beat his neighbor's Mustang in a drag race. Money was no object. The catch? It had to look completely stock from the outside. So what was actually going wrong with factory VW engines when pushed hard? Gonzalez identified 7 critical failure points. First, the pressed-together crankshaft would literally come apart at high RPM. The friction fit couldn't handle the rotational forces. Second, the connecting rods were designed for 4,000 RPM continuous operation. Push them to 6,000, and they'd stretch like taffy before snapping. Third, The cylinder heads couldn't flow enough air to support real power. The ports were tiny, the valves were shrouded, and the combustion chambers promoted detonation. Fourth, the valve train geometry was wrong. The rocker arms didn't maintain proper contact angles at higher lift, causing accelerated wear and valve float. Fifth, the cooling system was marginal even at stock power levels. Double the horsepower, and you'd melt pistons within minutes. Sixth, the case halves would literally split apart under high cylinder pressure. The magnesium alloy wasn't strong enough. And seventh, the oil system couldn't maintain pressure at high RPM, leading to bearing failure. Any one of these problems would destroy an engine. Gonzalez had to solve all 7 simultaneously. He started with the crankshaft. Instead of accepting the factory-pressed design, he commissioned a one-piece forged unit from a local aerospace supplier. But here's the genius part. He didn't just copy the stock dimensions, he increased the stroke from 69 mm to 82 mm. Combined with larger 92 mm pistons, this pushed displacement to 2,180 kg. That's a 45% increase in swept volume from an engine that still fit in the stock case. But wait, there's more. The longer stroke meant the pistons traveled faster, increasing stress on the connecting rods. So Gonzalez designed custom H-beam rods from chromoly steel, rated for 8,500 RPM. He had them machined to aerospace tolerances, plus or minus 0.1 grams between rods. This level of precision was unheard of in automotive applications at the time. Each rod cost more than a complete factory engine. And the cylinder heads required complete reimagination. Gonzalez spent 6 months flow testing different port shapes using a homemade flow bench built from a vacuum cleaner and manometers. He discovered the factory ports had a sharp 90-degree turn that killed airflow. By welding in material and reshaping the ports with a die grinder, he achieved a 40-degree angle that increased flow by 85%. The intake ports went from flowing 89 CFM to 165 CFM at 25 inches of water. The combustion chambers presented another challenge. Stock VW heads had a 58 cc chamber with the spark plug shrouded behind the exhaust valve. This caused incomplete combustion and detonation. Gonzalez machined the chambers to 51 cc, unshrouding the valves and relocating the spark plug to a more central position. He then polished the chambers to a mirror finish, eliminating hot spots that could trigger pre-ignition. Think about that for a second. He was achieving combustion chamber technology that wouldn't appear in production cars for another decade, using hand tools in a Mexico City garage. Nent in the valve train required complete re-engineering. Stock VW rocker arms had a 1.1 ratio, meaning the valve lifted exactly as much as the cam lobe height. Gonzalez calculated that a 1.41 ratio would optimize airflow without exceeding the physical limits of the valve springs. He designed new rocker arms with relocated pivot points, maintaining proper geometry throughout the lift cycle. The valves themselves were another story. Stock intake valves were 35.5 millimeters. Gonzalez fitted 40 millimeter stainless steel valves with narrowed stems for better flow. The exhaust valves went from 32 millimeter to 35.5 meters. The valve springs were custom wound from silicon chromium steel, maintaining proper seat pressure up to 7,500 RPM. Now here's the kicker. All these modifications generated massive heat. A stock Beetle engine producing 53 horsepower rejected about 70 horsepower worth of heat through the cooling fins. Gonzalez's 200 horsepower engine produced nearly 300 horsepower worth of waste heat. The stock cooling system would melt the engine in minutes. His solution was elegant. He increased the fin area on the cylinders and heads by 40% using deeper, more closely spaced fins. He modified the fan shroud to direct airflow more efficiently, sealing all the gaps that normally leaked cooling air. He increased the fan diameter from 100 mm to 200 mm and changed the blade angle for more airflow at lower RPM. The oil cooler went from 96 square inches to 225 square inches of surface area. He added a remote oil filter with a built-in thermostat, maintaining optimal oil temperature regardless of ambient conditions. But the real innovation was the cooling tin. Stock VW engines used simple sheet metal to direct air around the cylinders. Gonzalez fabricated complex ducting that created a venturi effect, accelerating airflow across the hottest parts of the engine. He incorporated adjustable flaps that could be tuned for different ambient temperatures and altitudes. The result? Cylinder head temperatures stayed below 350 degrees Fahrenheit even during extended full-throttle runs. Note the case halves required reinforcement to handle the increased cylinder pressure. Stock VW cases would crack between the cylinders at anything over 8.1 compression. Gonzalez was running 10.51. He solved this by installing steel cylinder sleeves that distributed the load across a larger area of the case. He also had the case halves welded and machined for perfect alignment, then installed hardened steel main bearing inserts instead of the factory direct aluminum bearings. Monchny, the oil system, got similar attention. He machined the oil passages to twice their stock diameter, reducing flow resistance. He installed a high-volume oil pump with hardened gears capable of maintaining 60 psi at 7,000 RPM. The oil pickup was extended and baffled to prevent starvation during hard acceleration. He even added an AccuSump, a pressurized oil reservoir that maintained pressure during cornering. And let me put that in perspective. In 1969, Formula One engines didn't have this level of oil system sophistication. The fuel system was where Gonzalez really showed his understanding of fluid dynamics. Instead of a single carburetor, he fitted dual 48mm Weber IDF carburetors. But here's the thing about carburetors. Bigger isn't always better. Large throttle bores kill low-speed velocity, making the engine sluggish off idle. Gonzalez solved this with progressive linkage that opened the secondary barrels only after the primaries reached 60% throttle. He also designed custom velocity stacks that created a ram air effect at specific RPM ranges, essentially supercharging the engine using its own intake pulses. The ignition system was revolutionary for its time. Stock VW distributors used mechanical advance weights that were either too aggressive or too conservative. Gonzalez mapped the ideal advance curve on a dynamometer, then modified the distributor with custom springs and weights to match. He was achieving programmed ignition timing decades before electronic engine management. The spark energy came from a high-output coil designed for aircraft engines, delivering 45,000 volts instead of the stock 20,000. The camshaft was perhaps his masterpiece. Stock VW cams had 225 degrees of duration and 0.33 inches of lift, conservative profiles designed for quiet operation and long life. Gonzalez ground his own cams with 296 degrees of duration and 0.525 inches of lift. But duration and lift only tell part of the story. The acceleration ramps, how quickly the valve opens and closes, were carefully calculated to maximize airflow without floating the valves. He used asymmetric lobes with slower opening ramps to reduce stress and faster closing ramps to improve cylinder filling. Assembly required obsessive attention to detail. Every component was balanced to within half a gram. The crankshaft was dynamically balanced at operating RPM. The connecting rods were weight-matched end for end. Even the pistons were matched for compression height within 0.01 inches. The engine was blueprinted, with every clearance set to optimal specifications rather than factory tolerances. The deck height was equalized on all four cylinders, ensuring identical compression ratios. The first engine took Gonzalez 8 months to complete. When he finally started it, the shop filled with the sound of mechanical violence. The valve train clattered like a machine gun. The cooling fan howled like a jet engine, but the engine held together. On the dynamometer, it produced 178 horsepower at 6,800 RPM. Not quite 200, but getting close. Carlos Gonzalez spent another 3 months refining the design. He discovered the exhaust system was choking the engine at high RPM. The stock muffler was designed to meet German noise regulations, not performance requirements. He fabricated a merged collector that balanced exhaust pulses between cylinders, then added a straight-through muffler with minimal restriction. He also ceramic-coated the exhaust components to reduce underhood temperatures. The intake manifolds were another restriction. The stock manifolds had sharp edges and rough casting marks that disrupted airflow. Gonzalez spent days with a die grinder, smoothing every surface and matching every port. He radiused the entries and exits, creating smooth transitions that maintained laminar flow. The difference was worth 8 horsepower on the dyno.nn. The second engine produced 196 horsepower at 7,200 RPM with 147 lb-ft of torque at 5,500 RPM. Close, but not quite 200. The breakthrough came from an unexpected source. Gonzalez noticed the engine ran stronger on cold mornings. The denser air was worth measurable power. He fabricated an airbox that drew cool air from outside the engine compartment, sealing it from the hot air around the engine. Combined with ram air tubes that pressurized the airbox at speed, this pushed power to 203 horsepower. But here's the thing about horsepower claims. Anyone can make them. Proving them is different. Gonzalez's wealthy customer arranged a public demonstration at the Autodromo Hermanos Rodriguez, Mexico City's Formula One track. He invited journalists, VW dealers, and skeptics from the Mexican racing community. The demonstration would include dyno runs, acceleration tests, and a 24-hour durability run at full throttle. The dyno session silenced the doubters immediately. With witnesses from 3 different automotive magazines, the engine produced 201.3 horsepower at 7,180 RPM. For comparison, a new Corvette's 350 cubic inch V8 made 300 horsepower, but weighed 3 times as much. On a power per liter basis, Gonzalez's engine embarrassed everything from Detroit to Siena, and the acceleration tests were even more impressive. Installed in a lightened Beetle weighing 1,650 pounds, the engine propelled the car to 60 mph in 5.8 seconds. The quarter mile fell in 12.7 seconds at 108 miles. A stock Beetle took 19 seconds to reach 60 miles and ran the quarter in 20 seconds at 68 miles. The transformation was absolute, but the durability test was what really proved Gonzalez's engineering. The engine was installed on a test stand and run at 6,000 RPM, wide-open throttle, for 24 consecutive hours. That's 8.64 million crankshaft revolutions. The only maintenance was adding fuel and checking oil level. After 24 hours, the engine was torn down for inspection. The bearings showed normal wear. The cylinders still had visible crosshatch marks. The valve seats were perfect. The engine could have been reassembled and run another 24 hours. Word of Gonzalez's achievement spread rapidly through the international VW community. Orders poured in from racers worldwide. But Gonzalez wasn't interested in just building engines for wealthy customers. He wanted to democratize performance. So he did something revolutionary for the time. He published his modifications. In a series of articles for Mexican automotive magazines, Gonzalez detailed every modification with engineering drawings and specifications. He explained the theory behind each change, the problems encountered, and the solutions developed. He didn't patent anything or keep trade secrets. His philosophy was simple: knowledge should be shared, not hoarded. The impact was immediate and global. Speed shops in California started offering a styled Mexican stroker kitsch based on Gonzalez's specifications. German tuners who had insisted such power was impossible suddenly discovered it was achievable. The entire VW performance industry pivoted from mild bolt-on modifications to serious internal engine work, and unchallenged, but Gonzalez wasn't done. If 200 horsepower was possible naturally aspirated, what about forced induction? In 1971, he began experimenting with supercharging. The challenge was heat management. Compressing air raises its temperature, and the VW engine was already at its thermal limits. Gonzalez developed an intercooler system using methanol injection to cool the charge air. The methanol also raised the effective octane rating, allowing higher boost pressure without detonation. Thus, the supercharged engine was devastating. Running 12 psi of boost, it produced 286 horsepower at 6,500 RPM with 245 lb-ft of torque at 4,000 RPM. But more importantly, it maintained stock-like drivability. The engine idled smoothly at 900 RPM and pulled cleanly from 2,000 RPM. You could drive it in traffic, then destroy Corvettes at the drag strip. The ultimate expression of Gonzalez's engineering came in 1973. A Brazilian aircraft manufacturer approached him about developing an engine for light aircraft. They needed 200 horsepower, exceptional reliability, and the ability to run at 75% power continuously. Gonzalez modified his design for aircraft use with dual ignition systems, a dry sump oil system, and reinforced components rated for 2,000 hours between overhauls. But the aircraft engine underwent rigorous certification testing. It was run at full power for 150 hours continuously. It was thermal cycled from 40 to 140 degrees Fahrenheit. It was subjected to 20 G loads in a centrifuge. It passed every test. By 1975, over 200 aircraft were flying with Gonzalez-designed engines. Several are still airworthy today, testament to the durability of his engineering. As the racing applications were equally impressive. Formula V had been using stock 1200cc VW engines, producing 40 horsepower. Gonzalez developed a legal modification package that increased power to 68 horsepower while maintaining reliability for a full race season. His engines won 3 consecutive Mexican championships and influenced Formula V engine development worldwide. In drag racing, Gonzalez-powered Beetles became legendary. They were giant killers, humiliating big block muscle cars with a fraction of the displacement. One famous example, a 1967 Beetle known as Herr El Cucaracha, ran 11.2 seconds at 118 mph using a naturally aspirated 2.3-liter Gonzalez engine, producing 240 horsepower. It became the first air-cooled VW to break into the 11-second range without nitrous or forced induction. But perhaps Gonzalez's greatest contribution was proving that engineering limits are often assumptions, not laws of physics. Volkswagen engineers said 100 horsepower was the absolute limit for reliability. They were thinking within the constraints of mass production, warranty requirements, and conservative German engineering philosophy. Gonzalez approached the problem differently. He asked not here's what's safe, but he asked what's possible. Then he engineered solutions to make the impossible reliable. And his influence extended far beyond Volkswagen engines. The principle of systematic weak point analysis and re-engineering became standard in motorsports. The idea of blueprinting engines, building them to optimal rather than acceptable tolerances, transformed the performance industry. His open-source approach to sharing knowledge preceded the Internet age by decades, but embodied the same spirit of collaborative improvement. And the economics were staggering. A complete Gonzalez engine cost about $8,000 in 1970 dollars, roughly $60,000 today. But compared to buying a Porsche or Ferrari with similar performance, it was a bargain. More importantly, it could be maintained by any competent VW mechanic using mostly standard parts. You didn't need a specialized dealer or exotic components shipped from Europe. The technological innovations were decades ahead of their time. Variable valve timing wouldn't appear in production cars until the 1980s, but Gonzalez was achieving similar results with mechanical means in 1969. Direct injection was considered cutting edge in the 2000s, but Gonzalez's port fuel injection systems achieved comparable efficiency in 1972. Thermal management strategies he developed are still used in air-cooled aircraft engines today. OUTSMARTED, the cultural impact was profound. In Mexico, Gonzalez became a folk hero, the mechanic who outsmarted German engineers. His success inspired a generation of Latin American engineers to question conventional wisdom and develop their own solutions. The modified Beetles became symbols of Mexican automotive ingenuity, competing successfully against European and American performance cars. By 1975, Gonzalez had built over 300 engines, each one slightly evolved from the last. He maintained detailed records of every modification, failure, and success. This database became invaluable to the VW performance community. When electronic engine management arrived in the 1980s, tuners used Gonzalez's mechanical maps as baselines for programming. The story took an interesting turn in 1976. Volkswagen of Mexico invited Gonzalez to tour their Puebla factory and meet with German engineers visiting from Wolfsburg. What was intended as a courtesy visit became a technical exchange. The Germans were astounded by Gonzalez's solutions to problems they hadn't even identified. Several of his innovations were quietly incorporated into late-model Type 4 engines, though VW never officially acknowledged his contributions. And Gonzalez continued developing engines until 1982, when health issues forced him to reduce his workload. By then, he had trained dozens of mechanics in his techniques, ensuring his knowledge wouldn't be lost. Many of these apprentices went on to establish their own performance shops, spreading Gonzalez's methods throughout Latin America and beyond. The engines themselves proved incredibly durable. A survey in 2010 found that over 60% of Gonzalez-built engines were still operational, many with over 100,000 miles. Several are in museums, including one at the Volkswagen Factory Museum in Wolfsburg, a belated recognition of his achievements. Others continue racing their distinctive sound, a harsh mechanical bark completely unlike a stock VW, still terrorizing drag strips. And modern engine builders using computer modeling and CNC machining have validated Gonzalez's designs. His port shapes are within 2% of computational fluid dynamics optimums. His cam profiles match what modern software calculates as ideal. His thermal management strategies remain textbook examples of air-cooled engine design. He achieved through intuition and experimentation what now requires supercomputers to calculate. The aftermarket industry Gonzalez inspired is now worth billions annually. Companies like CB Performance, SCAT, and Eagle Racing exist because Gonzalez proved there was a market for serious VW performance parts. The stroker crankshaft he pioneered is now standard in performance builds. His cylinder head modifications influenced every aftermarket head design. Even modern water-cooled VW engines benefit from principles he established. The philosophical implications are equally important. Gonzalez proved that innovation doesn't require massive corporate resources or advanced degrees. It requires curiosity, persistence, and willingness to challenge assumptions. He showed that technological leadership can come from unexpected places, not just Stuttgart or Detroit, but Mexico City. His open-source approach demonstrated that sharing knowledge multiplies innovation rather than diminishing competitive advantage. And in the end, Carlos Gonzalez didn't just build fast engines. He demolished the myth of engineering impossibility. Every time an engineer says something can't be done, remember the Mexican mechanic who extracted 200 horsepower from an engine Germans insisted couldn't exceed 100. Remember that specifications aren't laws of nature. They're challenges waiting for someone clever enough to overcome them. Gonzalez proved that with enough ingenuity, even the humblest economy car engine can become a giant killer. The next time you see a modified Beetle at a car show producing absurd horsepower from an air-cooled engine, know that it's possible because one mechanic in Mexico City refused to accept "weren't impossible" as an answer. He re-engineered every weak point, shared his knowledge freely, and transformed an entire industry through sheer determination and brilliance. What modifications have you seen that seemed impossible until someone proved otherwise? Drop a comment below and share your own stories of automotive innovation. And if you enjoyed this deep dive into engineering rebellion, make sure to subscribe for more stories of the innovations that changed automotive history. Until next time, remember, the only real limits are the ones we accept without questioning.